Good morning, everyone. Thank you for joining us today. My name is Phil, and I'm one of the senior ESM mentors. Casey.
And I'm Casey, and I'm a new mentor with ESM.
And today we're going to be focusing on math strategies for both the ACT and SAT exams. Now, there's a lot of overlap between the exams. So the strategies will be somewhat like test agnostic in the sense that like they'll be equally applicable to both exams. We do, if you look at our slides, you'll notice that we have mostly ACT slides. Frankly, that was just because I just happened to find those beforehand. So don't take that as any indication of these being more relevant for one exam over the other. It's just kind of coincidence or happenstance. So I'm going to share my screen. We'll get started. Okay. I'm hoping it's not showing green. Casey, can you see my screen now?
Yes.
Okay, cool. So as we said, today we're going to be doing ACT, SAT math strategies. And the little subtitle here is how to increase your efficiency and avoid getting stuck. And I think the second part there is actually really, really important, because what often happens is students will get on a problem and they'll be like, oh, I don't remember how to solve this problem. This was 2 years ago. I don't remember the equation for whatever you may be dealing with. And they kind of just throw up their hands and assume all hope is lost, and they either skip it or they spend way too long on it. And so hopefully by kind of employing some of these strategies, you can help avoid that situation and really minimize those missed opportunities on the test. So today, we're going to be discussing very briefly like the differences between strategies and what we call math content. And I think, again, what's another important thing to keep in mind is you as a student need to really practice these strategies and understand when they work for you and when, frankly, sometimes they may not be the best approach. There's a couple of problems that we'll look at today where the strategies that we're talking about actually can be somewhat time consuming. And if you know that, like if you have a good sense of or intuition for when they're effective, you can avoid getting, falling into that trap. And so the different strategies that we'll talk about, I mean, the first one is maybe a little bit less of a strategy and more just like a basic understanding you have to have in order to tackle some of these things. But that's translating from English to math. So kind of knowing when you're supposed to be doing a certain operation: addition, subtraction, multiplication, division. Choosing your own values, plug and chug, which is probably the one most people are familiar with, but we'll kind of hopefully discuss how you can identify those really quickly on the test. Calculator, or as we lovingly call it, grip and rip, estimation, and then this last one, which Casey and I are just kind of blanketly calling plugging in points on a curve, and hopefully that will make more sense in a minute. Okay, anything to add, Casey, before we move on?
Nope. I think we're gonna cover it as we go through.
Perfect. Sounds great. All right. So
to kind of start us off, how do these strategies that we're going to talk about kind of differ from just solving the problem? So we're kind of creating these two groups of ways to solve the problem, kind of algebraically, which is how you would solve a problem in math class, versus employing one of the strategies we're going to talk about. So if you think about whenever you learn a new math concept in class, you do a bunch of different problems that are kind of all employing the same concept, and you're really just practicing how to actually do the steps to solve the problem over and over again. But what if you get on the ACT and, like Phil said, you can't remember those specific steps? You see a problem and you've seen it before, but you can't actually remember those specific math class steps to solve it. And that's kind of where the strategies come in. So these are, instead of actually going through those algebraic steps that you learned in math class, you kind of have these techniques which can help you kind of round the corner without having to do those steps. So they're kind of a backup plan for if you run into a problem that you aren't sure right away how to solve. And in some instances, the strategies are actually a lot faster than solving the problem in the math class way. So they're actually the better way to solve the problem anyway. And how to determine whether you should solve a problem the math class way or use one of the strategies is really something that you just have to practice. And as you see more ACT or SAT math problems, it'll become a little more clear to you which ones it's worth it to just write it down and do it as you would in math class, and which ones it's worth kind of approaching it with a strategy.
Great. Yeah. One thing I'll kind of quickly add is I think the other thing to keep in mind is, depending upon your personal preferences, sometimes the strategies may make more sense. For me, for myself, for instance, I'm very much a fan of getting in and, just really diving into the algebra. For whatever reason, that just makes sense to me. But some people may, steer clear of that as much as possible. So try to kind of play to your strengths. And as Casey, kind of mentioned, a lot of this really comes down to practice. I kind of use the analogy of like riding a bike. When you first learn to ride a bike, you have to really conscientiously, think about everything you're doing with your feet, with your hands, your balance, all that kind of stuff. Over time, it just becomes kind of natural because you've built that intuition. Through practice, you've gained that experience, and you'll actually be able to navigate riding the bike, or in this case, what strategy should I use? So don't underestimate how effective it is just to get reps in doing these things and asking yourself, what strategy would be applicable, and is it the way to go for this particular problem? Cool. I guess with that being said, let's move on to our first category. So the first category, again, this is maybe not so much of a strategy, but it's very crucial. So we didn't want to skip over this or ignore it. And that is, again, translating from English to math. And really what this is making sure you understand what different terms mean on the test. So for addition, there's all kinds of terms, and we just selected a handful that we thought were the most likely to show up. So like sum, in all, total, increase by, more than, subtraction, minus, decrease by, difference, multiplication, product, times, x% of y. That's a really crucial one. And then division, per, each, quotient. I would say per is the one that students often get tripped up by. And I guess that the last thing, we didn't really, think to add this, but in my mind as I'm kind of talking, make sure you understand when something is code for equals, because that's a really important thing to be able to kind of like, as you're translating from, I kind of tell students from left to right as you work through a problem, kind of write down things as you go. And so when you see the word is, that's often code for equal sign. So let's take a look at a couple of examples real quick. The first one we have here, this is a problem that I think students really struggle with. The language is a
hard
little
problem.
yeah, it is. It's I feel like, I've been probably seeing this problem 100 times maybe at this point. I don't know, who knows, plenty of times. And I feel like every student I work with, at least the majority of them, have to deal with it or have to talk about this problem. And again, the idea is like, as you go through line by line, try to translate as you go, as opposed to reading the entire thing and then trying to kind of piece together. Now, there's a little bit of debate, and Casey, maybe you kind of disagree, or maybe you can add on to this. There's definitely room for debate there. Like, should you read the entire problem and then kind of summarize? But if you have already done that and then you go back through, then at the very least, maybe that's when you'll kind of read line by line and translate. So let's take a look at this and see what we can figure out. So a local bowling league established its handicap for bowlers who have an average of 200 or less as 75% of. So right off the bat, that screams to me multiplication. So what I'm going to do is I'm going to say 0.75, and multiplication, I'll just write parentheses. And if you think about it, if I've done everything right so far, if I'm, on the right track, there's really only one option that kind of makes sense at this point in time. You could make an argument for maybe like answer D, for example, because I do see 0.75 times A. So I guess there's, still two valid options here, but let's continue. Of the difference, okay, so difference, if we look back at the previous slide, we saw difference. We said difference between, but difference nonetheless. Difference of. So we're multiplying 0.75 times the difference of two things. So at that point in time, really the only option that makes sense, we can scratch out all of these, is answer E. And it's the difference between 200 and the bowler's average. And then they tell us later that A is the bowler's average. So I'm pretty confident at this point in time. I'd say, okay, that's the only answer that makes any sense. And that really just relied upon my ability to kind of translate these English terms into mathematical operations. I think, anything else that you want to add, Casey?
The only thing I would add is on a question like this, just maybe it was a little tricky at first to figure out where the introduction to the question stops and the actual equation begins. So you see like the first 200 and you might think, oh, is that going to be part of the equation? And that's where maybe reading the question all the way through and then the second time will really help you to be like, oh no, that 200 is all in describing the bowlers. I don't need to look at that one. I'll start my equation with the next number that I see. And whereas,
Yeah, absolutely. That's a great point. I think a lot of it, yeah, it really boils down to being able to recognize when you're going to actually start doing some math for sure. Cool. Great. All right. You want to take a look at the next one?
Yeah.
All right. Let's take a look at this one.
All right. Oh, I need to erase my previous mark. Okay. So similarly here, let's walk through and see when we start to identify math words. So we have the total cost of renting a car is $35 for each day. The car is rented plus, okay, so we already know what we already have $35 for each day. So we know for each is going to be multiplication. We've got our 35 times the number of days. We'll put that in parentheses. You have much better handwriting on this than me. And then we have plus, so that's obviously we've got addition there. And then we've got this 42.5 cents and then another for each. So we've got plus and since we did 35 as a whole number, we've got to do 5. And then we've got another for each, so we've got another multiplication there. And now this is miles. The car is driven, and then what is the total cost of renting the car for 6 days and driving 350 miles? And so now here, this is a 2-part question. So now that we've got our equation, then we know we've got to plug in our 6 for days. This is 6. And then our 350. And then here I would plug that out. So yeah, should I actually calculate?
I mean, I think, I think we can kind of trust our viewers to be able to tackle this.
Yes.
We'll be getting into some more calculator based stuff in a few minutes anyway. So, but yeah, so exactly, as Casey just said, you kind of churn through, translate it as you go, make sure you're paying attention. There's also, we're not going to talk about this today at all, but there's a very good discussion to be had for students who aren't super comfortable with like dimensional analysis, or sometimes it's called unit analysis. That's not terribly important for this problem, but that's something else that you can kind of consider. If you do struggle with these word problems, that's another aspect, like another tool that you can kind of, really use to your advantage if you get more comfortable with it. So anyways, if you kind of plug in all of the answers, the answer ends up being C here. Can I not? I don't know why that's not going. Yeah, anyways, I'm sure everyone can figure out what answer C is. So cool. Thank you, Casey. I think that was our last example for this. So I think the next topic, yeah, so choosing your own values. So this strategy here, I think, is one of the more important ones. And I also think it's one of the less commonly known methods or strategies, sorry. And basically what this is, as you can see here, is you're going to take, if you see a certain type of problem, if there's a problem that prompts you to think, oh, this may be a choosing your own values, you're going to choose values, numerical values for your variables, and then calculate, or evaluate the expression with those numbers plugged into the variables. And so language that you see in a problem is huge here. It's critical. What you almost always see, or at the very least, very, very often see, is something along the lines of which of the following is equivalent / equal to, and then they'll say something like the expression below, or whatever, something like that. And then another pretty strong giveaway is if there are variables in the question as well as variables in the answer choices. That's huge. If you see variables in the answer choices, that's almost always an opportunity to use this strategy. And then the other thing, the last thing I'll kind of mention here is that, like, if you're dealing with an expression as opposed to an equation, you're again probably likely, probably going to be able to use this strategy. And again, as we've said, and we'll say probably multiple times throughout the webinar, practice is really, really important here. So let's take a look at the first example and see how we can figure this out. So you can see here right off the bat, oh, that's weird. I don't know why it's not lining me right. Sorry, give me 1 second.
It's because I'm annotating.
Oh, okay. Okay, cool. I think we're good now. So for all positive x, which of the following is equal to? And you can see right off the bat, this is what we just saw in the previous slide. This is very, very common, right? And then they have this expression, and notice there's no equal sign. And I think that's something we should kind of just highlight real quickly. The difference, because we'll say this probably multiple times today, the difference between an expression and an equation. An expression is just, well, it's an expression involving variables and numbers, and some, maybe it's polynomials, maybe it's square roots, whatever it may be, right? Maybe it's trig related, whatever. An equation, it has an equal sign, right? It's kind of in the name, right? And it's important to make that distinction in your own mind. It's probably something we all kind of know, but we don't necessarily pay attention to. So for this problem, we have, not a terrible expression, but an expression nonetheless that a lot of students are probably not going to be thrilled to have to like do some algebraic manipulation on. And if you look at it, it's not as bad as it looks, but it may just cause students to just get anxious and nervous and maybe throw in the towel and move on. And oh, this is near the end of the test, so whatever, I'm just going to take a guess and move on. But if you actually use this strategy, it's actually not too bad. So what I'm going to do here, I'm going to choose, well, actually, let's take a look at the algebraic way, I guess. So we have 3 different expressions, right? We're adding them up. And so we're going to have to find a common denominator. The common denominator for this one is going to be 2x plus 4. Because if I multiply this by 2, I get 2x plus 4. And so I'm going to have to multiply the leftmost term by 2x plus 4 over 2x plus 4. No, remember, there's a little 1 hidden there. Plus, and then this term here, I have to multiply by 2. 3x times 2 over 2. And then the right-hand term, I don't do anything to. So 2x plus 4. So, if I kind of churn through, if I distribute the 2 here, I get 4x plus 8. I'm just going to put this all over one denominator, because that's the whole point, is to get a common denominator, excuse me. Plus this gives us 6x, and then the minus 6 stays as it is. So 2x plus 4. So if we add all of this up, if we combine like terms in the numerator, we get 10x, and then plus 8 and minus 6 gives us the plus 2 over the 2x plus 4. And actually, if you take one more step, because if you look at the answer choices, nothing matches up right off the bat. But we can factor a 2 out of the numerator and the denominator, and those cancel out. And we're just left with 5x plus 1 over x plus 2. So you can see what I mean, hopefully. Like, this isn't a terrible problem, but for those of you who may not feel comfortable doing this, and there's plenty of opportunities for mistakes. I mean, I'm kind of surprised I didn't make a mistake, to be honest, at some point in time along the way. All right, so there's all kinds of opportunities for mistakes. Maybe you're not super comfortable with this. So this is where the strategy could be really, really useful. So let's look at how that would play out. So again, what the idea here is, we're going to choose a value for x. In this case, there's only one variable, so it's relatively straightforward. And we're going to evaluate the initial expression and see what we get. So if I, there's definitely a couple of things you have to keep in mind. If you're dealing with like squares, or maybe a lot of multiplication with no real addition, you probably want to be careful and avoid using like 1. Sometimes even avoid using 2, because 2 squared is the same as 2 times 2, and so that could throw you off. But that's probably not terribly crucial here, because we do have a decent amount of addition and subtraction. So what I'm going to do is I'm just going to choose x equals, I mean, in my mind, I want to choose 0, but I'm going to just be a little safer and choose 1. So 2 plus, I plug in 1 here, I get 3, 1 on the bottom, 1 plus 2, that gives me 3, 1 here, that gives me 6 over 2 times 1 gives me 2 plus 4 gives me 6. So what I get is 2 plus 1 minus 1. So this ultimately gives me 2, assuming I haven't done any arithmetic incorrectly. And now my job is to say, okay, I know when I plug in 1 for x in the expression, I get 2. Whatever the correct answer is, better also give me 2. So let's figure that out. So I plug in 1 to a, I get 5 times 1 plus 1 over 1 plus 2. That gives me 5 plus 1 is 6 over 3, which gives me 2. So that's good. Now here's the one area you could get tripped up on. There's like a positive and a negative to the first answer giving me what I wanted. It may not be the correct answer. Now we know, again, assuming I did my algebra right, we know that the answer is A. But there are plenty of times when maybe 2 answers will give you 2. Like I could see a scenario where if I plug in 1 here, I get 8, and maybe this was 2x plus 2, right? So I'd get 8 over 4, and that would also give me 2. So what you have to be careful with is don't just assume that because you got the right answer, or the desired answer, that the answer you're looking at is the correct one. You'll have to make sure you check other answers. That's where this can be a little time consuming. So again, I think it really makes sense for a lot of students, or not for a lot of students, for everyone, to really play with this and kind of get comfortable with when it would make sense. And like Casey said earlier, this is often a backup plan. If you're comfortable, combining these fractions and simplifying, I would say it's definitely the way to go. Because what if the answer wasn't A? What if A gave me, instead of giving me 2, it gave me 7, right? Then I would have to try B and potentially C and potentially D. And the worst case scenario is if the answer was E. That would be horrific. So again, keep in mind the point of these strategies is they're not always the best way to solve a problem, but they can, sometimes they are, but at the very least, they're a backup plan. Okay. Anything else that you'd like to add to that one, Casey?
Just that kind of as we did in this one, this is also a great strategy for checking your answer, which is kind of how we used it here almost. So if you do go through all the algebra and you have extra time and you just, you're feeling a little uneasy, you can also just choose your own value just to check. And then absolutely the expression and your answer should give you the same result after you plug in x equals 1. And if they don't, then you know that you've done something wrong in your algebra.
Yeah. It's the whole adage, like getting the same answer is a necessary but maybe not sufficient, maybe is necessary but maybe not sufficient. Like you said, you'll still have to check other answers, which is the downside to this. But okay, do you want to tackle the next one?
Yeah.
Cool. Oh, this is a good one. I love this one. I'm jealous.
All right, so do we want to start by solving it in the math class way first?
Sure, yeah, that sounds great.
Okay, so this one you might look at and be like, how do I solve this in the math class way? And what we want to notice is that we have some value squared, which we see the non-squared version in the second term, and then to no power in the third term. So we actually just have this, you can think of it similar to if this was x squared minus 8x plus 16, just with an extra x there. So we're going to factor it just like we would factor something like that, where we're going to have two terms with x, two factors with x squared. And then if you remember factoring, we need something that adds to 16 or multiplies to 16 and adds to -8, which pretty quickly we know is going to be -4 and -4. So that, which obviously simplifies to the x minus 4. Oh, wait, no, I lied. Did I do this wrong? No.
No, you're right.
Yeah. Oh, yeah. Yes. Oh, yeah. Okay. Yes. Because now what do we have? We have two differences of squares. So we can simplify this even more. And right, because x squared is a squared and 4 is a squared. So then what do we have? We have x plus 2, x minus 2. And then that same thing again for this term. So we can square. Okay. Okay, which ultimately gives us A, not D. Okay, so you see, even doing it algebraically, I wanted to make a mistake and just jump to the end without finishing factoring it out. So now let's do it where we pick our own values. So like Phil said, because now we have x to a power, we're a little hesitant maybe using 1 or 2. It would probably work here, but let's just jump to using 3, which is going to make these numbers kind of big, but we can still do it. So 3 to the 4th is going to be what, 81. And then we're going to have minus, and then 8 times, these are going to be big numbers. 3 squared is going to be 9, and then plus 16. So 8 times 9 is 72. So we have 81 minus 72 plus 16, which is going to be what we've got. 81 minus 72 is 9, plus 16 is going to give us 25. Okay, and then now let's plug 3 into the answer that we got. So we're going to get 3 minus 2 squared and 3 plus squared, which this will give us 1 squared, which is going to be 1 times, this gives us 5 squared, which is our 25. So we do indeed get the right answer there. So then we know, again, if we would have picked 3 as our plug in our own, or choose our own value, that gives us that A is the right answer. Now let's look at some of these other ones. 3 again is kind of a big number, so we start to get ugly with the to the 4th power. Well, let's look at B. So if we plug in 3 here, we instantly can see that this is not the right answer, right? Because you're going to get 3 minus 4. That'll give us, and if we remember, D is the one I wanted it to be at first. So you get 3 minus 4, that gives you negative 1 to the 4th, which is never going to be 25. So we know it can't be D. Similarly, if we look at C, we're going to get 3 minus 2, which gives us 1 again to the 4th is going to be 1, absolutely not 25. And then we've got B, a little uglier. Let's see, we've got 9 plus 4. So we're going to get 15 here, a 5. We already should be able to tell that this is not going to give us, and then a 1. So none of the other answers give us 25. So here, A would be our only answer.
Awesome. Yeah, thank you. And then I guess the one thing I'll add is Casey and I, we talked about this yesterday, and we kind of discussed how, like, when you are choosing your own values, as Casey did, it kind of sometimes will make sense to be a little conservative. I think this one, because as Casey, saw, as she demonstrated, or as Casey demonstrated, like, 3 wasn't a ton of fun to deal with, right? It wasn't the best number to choose, but there was the reason, why we chose that, to be conservative. If you look at this actually could be done by choosing 0 or 1. The downside to choosing 0, if you plug in 0 to the initial expression, you get 16. And if you plug in 0 to the other expressions, 2 answers will also give you 16. And so you'd have to then decide, okay, well, what do I do from there? The next logical step would be choose another value. Choose 1, for example. And the reason why 0 and 1 work, we kind of, again, we try to hesitate about using them, but they can work okay. They usually would work okay in this scenario because we're dealing with addition. You have one term plus another plus another. Where it gets really tricky, where it gets a little dangerous to do that, is if you have something like this: x squared y cubed, z to the 4th over x to the 3rd, y to the negative 2, z to the 5th, or something like that, right? And this one you may look at this and you may just absolutely want to run and scream and hide. Plugging in, choosing your own values could still work here, but this is where you'd want to be careful with, maybe 0 and 1 don't work very well, because 0 just kind of kills everything, and obviously you'll run into an issue in the denominator, right? 1 doesn't really do anything. Nothing interesting happens with 1 because you just get 1, 1, 1. So this is a really prime example where choosing slightly larger values will be crucial. And hopefully, if you're taking SAT, this would be on the calculator section, so you could tackle that. We see here, this is actually from a no calculator section. So, Casey was a hero and had to, churn through using 3. Like I said, we wanted to kind of demonstrate that kind of aspect of this strategy. So cool. I think anything else you want to add before we move on?
I think we got it.
Perfect. All right, let's look at the next one. So the next one, this one here, I think is, we threw this one in just to kind of show how, in this case, actually knowing the rules is going to be far, far superior. But that being said, you could still, work this both ways. We'll leave this, for you guys if you guys want to consider this later. I think we've probably demonstrated this thoroughly enough. I feel like, unless anyone's really dying for us to do this one. Just know your rules of exponents and how like bases, how exponents translate there. Okay, next strategy that we want to discuss today is plug and chug. And this is, again, as we mentioned in the beginning, this is the one most of you are probably familiar with. This is something that, everyone kind of learns how to do at some point in time, because, math can be frustrating. So you want to try to, recognize any solution possible. And this is basically, if you have an equation, right? And again, an equation, has an equal sign, and the answer choices are numerical. There's no variables in the answer choices. Then this is probably a prime candidate for that. Now, again, it's likely a backup plan, but it's definitely an option. And sometimes, it may not be a backup plan. Maybe the algebra is really obnoxious. So maybe this is actually the best way to go. So let's take a look at some examples. So this first one here, I think this is a pretty good example where using this strategy can be really beneficial. So let's kind of walk through both ways to do it. Again, we'll just do the algebraic way. So what I'm going to do is multiply both sides by 5 squared. And again, as we saw, as we alluded to in the previous problem, if we know that these are the same base, we can just, use our rules of exponents and we can add the exponents. So this is 5 to the power of 6. And then the next thing I'm going to do is recognize that this can be written as 5 squared. And so I have 5 to the power of 6. And then this here and this will combine, we'll multiply those. We get 5 to the power of 2x is equal to 5 to the power of 6. And once we have that, since they're the same base, we can set the exponents equal to each other. And we get x is equal to 3. And that's the final answer. Now, what did I have to do? I had to know how to, add exponents here. Again, if the bases are the same, I had to recognize that 25 is 5 squared. And then I had to recognize that I can multiply these two to get 2 to the 2 times x. And then, the last step is not such a stretch, but you then had to recognize that, oh, okay, that has to be, equal to each other. And again, not terrible, but if you're not super comfortable with those rules, those, concepts, this is where plugging and chugging could be really, really helpful. So I would grab my calculator. This is the ACT. Again, I said, we're talking test agnostic, but if you're on the ACT, you should know, grab a calculator, plug in 3 here, right? So 25 to the power of 3 over 5 squared. And then, okay, what is this? Divide by that, and then you'll get some value, right? I guess this should just be, I guess it should be 5 to the 4th. Duh. So this should be 5 to the 4th, and then, make sure that whatever this number spits out, that you get the same thing here. Fortunately, because, we happen to choose a nice answer or nice question, the first answer would work. But I think being able to recognize you could go either way in this problem is really, really important. Again, we'll talk a little bit. There's a few calculator things we'll discuss today, so I didn't want to grab the calculator just yet. But anything to add to that? I think that one's fairly straightforward.
I think that one was pretty straightforward. Yeah.
Cool. All right. Do you want to grab the next one?
Yes. All right. So this one, it's not, you can make the argument to either just math class your way through it or to plug answers in. So this is a good one where as you do a lot of practice and preparing for the ACT or the SAT, you should know yourself well enough to know, hey, I'm really comfortable with distribution. I never lose a negative sign when I distribute. I'm good with this one. Or, you know, sometimes I am forgetting to multiply my negative sign through and make little mistakes. So maybe I'm gonna plug and chug, or I'll check my answer with plug and chug, which is always, I always recommend checking your answer if you have the time. Do both ways. Okay, so let's algebra through this one first. So we're gonna have multiple times where we need to distribute, right? So remember, distributing is being multiplied to both. So I'm just gonna do all of those here in one step. So we're gonna have 14x minus 35. And then remember, whenever we distribute a negative, distribute this as if it were -2. So we get minus 4x, and then a minus times a minus, so then plus 10. And then that equals, and then we distribute on this side too, 4x plus. And now we just have to get the x's on one side and the numbers on the other side. So we'll subtract a 14x, add a 4x, both sides. So then what do we get? We get 8x minus 14x on this side, which is -6x. And then we want to subtract our 20 from this side. And so then we have -20 minus 35 plus 10. So we end up with minus 55 plus 10. So minus 45. 6x. No, okay, yeah. And then you divide by -6, divide by -6. Okay, and then here, so we instantly notice that this is not matching any of our answers, but we should be able to see that both negatives are going to cancel, obviously. And then both of these have a factor of 3, so we've got to simplify our answer, which will ultimately get us down to 15. 6 is 3 times 2, and 45 is 3 times 45. Okay, so that was a little annoying. We had to do lots of multiplication and addition. So let's look at what would happen if we just try to start plugging answers in. And it's also going to be not that quick because we see we've got a lot of x's, which means we have to plug it in a lot of places. Okay, so let's start with A, which is really easy. It's just 1. So if we plug in 1 to our first parentheses, we're going to get 2 minus 5. So we get a -3 times 7, and then minus, I should erase this. Get a -2 times, we plug in 1 here, we get 2 minus 5, so another -3, and then equals 4. And then 1 plus 5, so 6. So what are we going to get? We're going to get -21 plus 6 equals 24, which we know that that's not true. So no, it's not 1. We'll do B, and then I'll leave plugging in C and D to the viewer. Okay, so we're going to do the same thing here, but now we're plugging in a fraction, which is why you can see how plug and chug here gets a little frustrating because now you have to deal with fractions. But as you'll see, it's not the end of the world. Okay, so again, we've got 7, and now we're going to have 2 times 15 halves minus 5 minus 2 times another 2 times 15 halves. Again, minus 5. So if you notice the pattern, you could only do that once and just use the same value twice. And then that's going to equal for, I'm running out of space here, 15 halves plus. So on the left side of our equation, we're lucky because we're multiplying 2 times 15 halves. So we kind of get rid of our, we get rid of our fraction whenever we multiply those. Then we're left with 15 minus 5, which is 10. 7 times 10 is 70 minus, and then again, we have another 15 minus 5, so we get another 10. So we get minus 20. And then the right-hand side, we're still going to have that fraction. So we're going to get 15 halves plus 5. So let's just quickly think of what that is. We've got to get a common denominator. So we're going to have 15 halves plus 10 halves. So we'll get 25 halves times 4. So that'll give us 100 halves. And then quickly you can see that both sides are 50. So we see that B does indeed give us left and right side equal on the equation. So good. But you can see that neither of these were super easy. And plug and chug didn't really save us that much algebra. We still had to deal with distributing, adding, an equal number of times. So this is kind of an example where the strategy isn't going to save you any time. So it's really a matter of what do you feel most comfortable with. You feel really comfortable with dealing with variables and distributing and adding with variables and ultimately solving the equation, do it that way. Whereas if you're like, oh my gosh, the X's are freaking me out, I don't like them, then plug and chug is probably the way to go.
Awesome. Thank you. And then one thing I'll add, which I don't think we mentioned, the good thing about plug and chug versus like the other strategy, choosing your own values, is if you get the right answer, or I should say, if you get a statement that's not a contradiction, you got 50 is equal to 50, you know that has to be the right answer, because this is different from the previous types of questions where potentially because of the value that you chose to plug in for the variable, there could be two answers that give you the desired result. Here, if you get the correct answer, I keep saying correct, if you get the desired result, if you get something that's not a contradiction, it is the correct answer. So, Casey mentioned, oh, you can try C and D. In theory, you wouldn't have to. You'd be like, okay, cool, 15/2 works, so I'm done. And so that's, yeah, the algebra kind of sucked here either way, but that is the silver lining here, is if you stumble across the correct answer, it is the correct answer. Awesome. Thank you, Casey. Okay. This one here, I think this is a great example where actually plugging and chugging is pretty rough. Now, again, we're kind of fortunate that the questions that we selected, if you were to plug and chug, for this one, just spoiler alert, the answer is F. So if you were to plug and chug, F would show up and you'd be like, okay, cool, I'm good. So let's see how that works real quick. So basically I would just plug in -8. So x squared minus 2x minus 8 is equal to 0. And again, now this boils down to factoring. Now, factoring, or if you're not super comfortable with factoring, what's your backup? Pretty much always quadratic equation, which we'll get to in a second. But for this, you can just say, okay, this is going to be x. I have to have x squared, right? Two numbers that multiply to -8 and add to -2. Well, that's going to be -4 and +2 equals 0. Set each of these individually to 0 and solve. So this gives us x is equal to 4. X plus 2 equals 0 gives us x is equal to -2. And so we get what we want with the first answer. So plugging and chugging is actually not terrible here. But if this wasn't the case, if answer K was the right answer, this would be, I don't know if I want to factor multiple times, potentially five times, right? Or, again, if you're not super confident with factoring, using the quadratic equation multiple times. That being said, let's look at how you could solve this from a more kind of traditional, and maybe not, I don't know, traditional is maybe not the right term, but more of an algebraic way. So what I know is if I can't factor something, as we mentioned earlier, I have to resort to the quadratic equation. So let's see how that works. So negative of -2 plus or minus the square root of -2 squared minus 4 times 1 times n. And this is equal to, over 2 times 1. This is, these are the values of x, right? So if I kind of simplify, I get 2 plus or minus the square root of 4 minus 4n all over 2, and that's equal to x. And what I can do at this point is I can set x to one of these values. So I can say 4 is equal to 2 plus or minus the square root of 4 minus 4n all over 2, and then solve. And if you do this, you'll end up getting -8 for n. Again, assuming you do everything correctly. So this is an example where it actually isn't that bad in practice because plugging and chugging worked on the first answer. But if that wasn't the case, which there's no guarantee that that will be the case, you can imagine going through potentially five different. I guess you'd only have to go through 4 if you trust your algebra, because if you get 4 incorrect answers, then the fifth is correct, of course. But still, 4 quadratic equations or 4 factoring, 4 different instances where you have to factor, that could be a lot. It could be annoying. So again, as everything we've been discussing today, it's really, really important to kind of understand your preferences and your personal strengths. Anything to add to that, Casey?
No, I think we covered plug and chug pretty
Cool.
well. And again,
Cool.
like you said, this is probably something that you have used before. So don't overthink it too much. It's just the same way that you've used plug and chug in the past.
Yeah, exactly. I think that the key component here is because you're dealing with a test that's fairly static, SAT or ACT, you're going to see similar types of questions over and over, and you can hopefully gain some experience and learn when it's best to use this strategy. One other quick comment I forgot to make at the beginning of this. We're going to leave about 5 minutes at the end to just talk about certain things, or sorry, for you guys to ask any questions you may have. But if you have questions, feel free to throw them in the chat room. We'll do our best to kind of monitor that and respond as we can. Okay, so let's continue on. Calculator. So this is, I've been kind of teasing this. So exciting. I've been teasing this for a while now.
We all love our calculators.
We all love our calculators. Yeah. For this section, we are going to be focusing on the TI-84. We found it's obviously just going to be easiest to focus on one calculator. And that is the standard calculator for most students taking this test. If you don't have the TI-84, if you use like an Inspire that's allowed to, that you're allowed to use, just keep in mind it could probably do the same thing. If you're using a scientific calculator, some of these things may not be applicable, but we have a couple of things that we just wanted to mention really quickly. But the big picture here is that your calculator is a tool for a reason, like it has a purpose, and knowing when to use it effectively is incredibly beneficial. There are certain times where you may look at a problem, you're like, oh my God, there's going to be a ton of algebra here. But maybe your calculator can cut down on that. Maybe actually just grabbing your calculator can, cut through a lot of the algebraic clutter. Also, as long as you're comfortable and careful with your calculator, it can ensure a higher level of efficiency, I guess, and a higher hit rate. It avoids mistakes with the algebra potentially. So let's look at our first example. And this one I love. I'm actually going to share, give me 1 second. I'm going to share my desktop so you can see my calculator at the same time. Okay. Casey, can you confirm that you can see the calculator too?
Yes.
Cool. Perfect. Thank you. So this one here, I love this problem for a couple of reasons. First and foremost, I like complex numbers. That's my own personal thing, I guess. But more importantly, this is a great problem where, students, again, some students will struggle with complex numbers. And if that's you, this would be really, really beneficial. Your TI-84 can tackle this problem very, very easily. So instead of, going through and actually, expanding the terms and foiling, right? And you can go through all that. It's not terrible, but again, some students may not like this. And your calculator is going to, hopefully give you more confidence. You can actually use your calculator to solve this problem. So if you look at the bottom, right above the decimal point, there's this little blue I. If you click second first, and then click the decimal, that gives you I. And your calculator can, handle all of the operations with complex numbers very, very nicely. So I'm just going to plug this in real quick. Hit that, hit enter, and it gives me 13 plus 84i, and I move on, right? So keep in mind, it took me a while to type that in because I'm using my mouse. It's a lot faster if you're on, just use if you got the physical calculator in front of you. So that may have seemed a little lethargic, but it's actually a lot faster in practice when you have a physical calculator. And again, it avoids certain mistakes, right? Foiling is not terrible, but it's definitely, brings opportunities for mistakes. If you forget that when you, get 36i squared, some students forget what they have to do with this, right? That turns into negative 1. I almost said negative I, right? So, and then you have negative 36 roaming around and 49 and, 42, 84 I guess I should have looked there. So now you have to do a little bit of, it's very basic arithmetic, but it's like there's a lot of steps, both algebraically and arithmetically, that you had to run through when you could have just done this on your calculator. And you can be pretty confident that your calculator gave you the right answer. Anything to add there, Casey?
Nope. Yeah, I think this one, is an obvious choice for the calculator.
Yeah.
And again, as always, if you have already went through and solved it by hand and you just want to check your answer, you can always go back and then put it in your calculator too, and just make sure that what you got whenever you foiled it out matches what your calculator says.
Cool. All right, let's look at the next one. All right. I guess I think I'll take this one since I have the calculator pulled up. This one here, the reason why we consider this a calculator problem is the calculator is not really doing anything like magical. Like the calculator is just gonna be performing what you want it to do. I guess that's kind of obvious, I guess. But what I mean by this is the following. So which of the following operations will produce the largest result when substituted for the blank in the expression 14 blank negative 1 over 40? And you can kind of churn through this mentally and kind of conceptually, like ask yourself, okay, what would happen if I added a negative number? What would happen if I subtract a negative number? What would happen if I divide by this, blah, 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 blah. But at the end of the day, you can actually just go and say, you know what, I'm just going to see what happens. Like if I do 14 plus negative 1 divided by 40, and then your calculator, will give you an answer. Okay, 13.975, and then just leave that there, right? Don't do anything with it. Just now go to the next one. 14 minus negative 1 over, oops. You can see how this is a little clunky, so I apologize. It'll be faster with your own calculator, right? 14.025. Okay, so we obviously know that F couldn't possibly be it because we've already bested F with the first one, right? 14 divided by negative 1 over 40. And here you get negative 560. And now this is a point that we should kind of touch on real quick. So students may look at this and be like, oh, well, that's a big number, right? 560 is way bigger than 14.025. But obviously, it's negative. So the question is, well, what are they looking for here? Do they want the largest? And the term I'm about to use is the clue. Do they want the largest in magnitude, or do they want the largest result? If they don't say magnitude, you can just assume the most positive number is what they're looking for. When they say largest, they just mean most positive, unless they specify largest magnitude. Because the magnitude, another term that you may or may be more familiar, maybe not more familiar with, is absolute value. So magnitude, absolute value, they're more or less synonymous in this case. So if they don't say absolute value or magnitude, you're thinking, the thought is that you're looking for the largest positive number, or the most positive number, excuse me. So anyways, I'll kind of spare you the last two things. I guess the only comment I'll make here is understand, because multiplication, that's pretty obvious what that is. Averaged with just means 14 plus negative 1 over 40 divided by 2. When you have two numbers, what it means to average them means to average them, add them together, and divide by 2. Cool. So hopefully that this calculator can help you, when it's appropriate, just kind of cut through some of the clutter. I've seen so many students kind of pour over this problem and like really get themselves like caught up in a loop, basically, because they're like, well, what if this? What if this? What if this? And it's like, okay, we'll distill it to its simplest form. You're just performing these operations on these two values. Let your calculator do the legwork, and then your calculator will get you through it. All right, I think that was. Oh yeah, we do have one more calculator example. So again, Casey, if you're not too upset, I'll finish this off since I've got the calculator. This is another good example where you may or may not be super confident dealing with radicals and how to pull values out. It's not too terrible, so I think this is something where it could go either way depending upon your personal preferences. But root 2, I'm just gonna leave that as is. Root 8, well, that's 2 times 2 times 2, 2 times 2 times 2, and then 18 is 9 times 2, or 3 times 3 times 2, right? And if you remember correctly, whenever you have two copies of a value, you can pull them out. You pull them out as a singular value though. So this is root 2 plus 2 root 2 plus 3 root 2. And now we have 1, 2, and 3 copies of root 2 that we're going to add together. So we get 6 root 2. So the answer here is G. And you can see, not terrible. But again, if that's something that you're not super confident with, just grab your calculator, plug these all in. The downside is because they're not in decimal form, or sorry, because your calculator, well, actually, I think it's my calculator. I actually think my calculator is set up to, oops, that's not what I do, sorry. I think my calculator is going to spit out a decimal, which is fine. The downside to that, though, is that you're going to have to match up the answers by evaluating the other ones, the answer choices in your calculator. And again, I apologize. I know it's kind of obnoxious for me to click through. It's slow and clunky. So 8.48, whatever, blah, blah, blah. You'd go through it, and maybe you can get rid of some. Obviously, you can get rid of K, right? You can probably get rid of J and probably get rid of H if you think about it, because root 2 is greater than 1. So you're multiplying 12 and 14 by a number greater than 1. So that's going to be out of the, out of the loop. So maybe you actually only have to evaluate F or G. If you evaluate F and you don't get 8.48, then it's G, and vice versa. If you evaluate G and it is, So it may not be as bad as I kind of initially said, but you do have to kind of apply a little bit of consideration there. So, okay, so we are getting up to the time. So I'm going to push through a little bit. I do want to leave a few minutes. We may go over an hour a little bit. That's okay. But estimation, this is the next strategy that we wanted to discuss. And Casey, if you want to jump in, feel free. I'm just going to try to push through for a few minutes real quick. So estimation, this is a great example of a problem that, a strategy that can be used as a nice backup if you're completely lost. So often this is really important or really helpful for like geometric problems when there's a figure that's given. Even if you don't have a figure, drawing your own figure can be really helpful. But the idea that the figures on the ACT and SAT are not drawn to scale, they kind of make that little, well, the ACT I think says that they are, but the SAT they say don't assume. But usually they're very, very close to scale at the very least. So you can trust them pretty reliably. This is a great example here. We have a hexagon that is inscribed within a circle, and they're asking what is the perimeter of the hexagon. And if you're not super confident, you may look at this and be like, I have no idea how to figure out, because the idea is, obviously figure out this leg and then multiply by 6, right? And you may ask yourself, well, how am I supposed to do that? And you can go through the whole process of where you kind of break this up and you say, okay, well, this is 360 divided by 6. So each of these is 60, and this is the same length as this. So you kind of figure out, okay, this is 60 and this is 60. So that means all of these are 10, right? 10 times 6 gives you 60. But if you just look at it, what does the side look very, very close to? It looks, it's technically supposed to be the same length, right? It looks very, very close to the lengths of the outside legs. So if you were in a pinch and you didn't really know how to go through the geometrical kind of, proof that I just went through, you can just say, okay, well, this is probably pretty close to 10. So multiply that by 6, that gets rid of this, right? And if it's close to 10 and I'm multiplying by 6, this probably seems a little too big. So maybe you're at least down to 50 or down to 1 of 3. But if you were like, oh, that looks really, really close, this would probably be the best guess. So estimation, super, super important. This one here, another great example, where if you're not entirely sure, really the only information you're given is 145 and the 90 degrees here. And they're asking you, what is the measure of CED? So this angle here. And you may ask yourself, I have no idea how to get there, right? Well, if you look at the angle itself, it's pretty clear it's not 90 degrees. So it's not even close to 90 degrees, excuse me. So it's probably not 80. And then it looks to be, substantially bigger than 35. So I would probably get rid of that, right? Like you can go through this process where you're just kind of getting rid of answers that don't seem reasonable. And at the very least, maybe, I don't want to say never assume that this is the case, because it sometimes is the case, but in this problem, if we're estimating, I'd probably discount that, because what else am I going to do here, right? So maybe now you're down to 50-50 and, hopefully you guess C, right? Again, I'm gonna, there's obviously a way to go through this more rigorously, but that's not the point of these examples. Okay, I'm gonna skip that. The last thing, let's see if there are any questions. I don't think there are any right now. So the last thing I want to talk about is plugging points on a curve into answers. So basically, we'll kind of just skip to the punchline here. You're given a curve. In this case, we have an ellipse, and the next problem that we'll look at very briefly is a hyperbola. These are both, conic sections, and sometimes students haven't seen conic sections, or if they've seen them, they, run in terror because they're horrible and they just hate everything about them and they don't remember them, right? You don't remember how to actually generate the equation for an ellipse given certain aspects. Like in this case, we have the semi-minor, semi-major, right? All that kind of stuff. We have the center, and like maybe all of that is great, but you're like, I don't know what to do with that information. But keep in mind, one of the things you can always do with a problem like this is if you're given a point and you plug in X and Y into an equation, the left-hand side should equal the right-hand side if it's the correct answer, right? And so if I plug in 4, 0, and you can the nice thing is you can go through a couple of these fairly quickly. If I plug in 4 here, 4 plus 4 is 8 squared, 64, but I'm going to be adding something to that, and it's a non-negative value, so that's out, right? If I plug in 4 here, that gives me 0, so that term's gone. But if I plug in 0 here, I get -7 squared is 49. 49 is obviously not equal to 1, so you can get rid of that one. If you go on, 4 squared over 16, that's 16 over 16. That's, that's 1, right? 0 squared, excuse me, over 49 is 0. So that's 1. So that's comforting, right? That's likely the answer. But you go through 4 squared, I'll just say like maybe 4 squared, 16 over 8, 2. And again, I'm adding a non-negative value to this. So I'm just going to get bigger than 2 at the very least. So that's out. Here, 4 squared is 16 over 4 is 4 again. And again, I'm adding a non-negative value. So, okay, cool. The answer must be C. I didn't have to know much about ellipses at all. And then basically here is the same thing. This one's a little more complicated because one point, for instance, if we chose this point here, it only gets you down to one of 2 answers. So what you would do at that point in time is maybe try, oh, well, look at it passes to the origin. So maybe plug in 0, 0 as well. The other thing too, is you can get rid of a couple of answers, D and E, if you recognize that hyperbola is the X term minus the Y term. And so that gets rid of D and E, and then at least you're only plugging in the values into one of the 3 answers. So sorry, Casey, I kind of blitzed through that. Anything you'd like to add?
Not really. Just that with the point of this estimating points on a curve is that if you see a graph of something that you aren't familiar with, don't panic. Use this strategy, and you can hopefully at least, like Phil was saying, eliminate it down to 2 answers, and then you got a 50-50 chance, which is much better than a 1 in 5 chance.
Yeah. And again, I think this is an opportunity for students to maybe take a shot at problems that they wouldn't otherwise be able to tackle. 53, it's late in the test, maybe you're a little flustered. I don't blame you. Maybe you haven't seen hyperbolas, maybe you haven't seen them in a while. This is an opportunity where maybe you think this isn't a problem you could ever get, and you're like, wait a minute, I can just plug in a point and see if I get a contradiction or not. And that's pretty straightforward. That's pretty easy. You've got your calculator, at least for the ACT in this case. You've got your calculator, right? And the arithmetic and the algebra, it's really actually, I guess, arithmetic. The arithmetic's not terrible. So, it's an opportunity for you to gain a point that you otherwise would have potentially, just passed up. Okay. Anything you want to close with, Casey? I think we're going to take a few minutes for questions if anyone has any questions, but.
Yeah, I think the big takeaway is what we've been saying the whole time is really just these strategies are pretty much meant as backup plans. So for when you run into a problem that you either don't know how to solve, or you feel like the algebra is gonna be trife with error, and you think you're gonna make mistakes, or you feel uncertain in your ability to solve it algebraically or the math class way, then look into these. And especially if you're taking a test soon, and this is the first time that you're hearing of these strategies, don't let them cloud your own knowledge of how to do the problem in the math class way. But with a lot of practice, you might find yourself choosing a strategy over the math class way just because it does save you a little bit. That was a really roundabout way of saying with practice, you know, it will help you to figure out, should I use a strategy or should I just chug through this algebraically.
Awesome. Thank you. Yeah, so thank you to everyone. If you have any further questions, I'm going to leave this open for another couple minutes. If there's anyone who does have any questions, now is the time to answer or ask those questions. If you have any questions beyond the scope of this, webinar, feel free to always reach out to us at any point in time. Otherwise, thank you so much and take care.